Hello, ELT132. This is Roger Young. And this video is going to discuss two types of counters. One is called a ring counter and one is called a Johnson counter. They're quite straightforward, which is really good, right? They're not hard to understand. So if you look at these, you have a bunch of D flip-flops, right? And by the way, if you look at this line, it's coming right in to D, right? And the output comes out of Q, and it continues all the way around here, right? So if you think about it, this flip-flop right here, the output swings all the way around and becomes the input of the flip-flop on the left. Obviously, this flip-flop right here feeds this flip-flop right here. The output of this flip-flop goes to the D input of this one. That's a D, right? The Q output of this one goes into the D input here. And the output of this one goes into the D input here of the last one on the right. And then it just comes around, all right? Now, this is a representation of this. If you have, suppose this is a 1, in other words, this one right here, the Q output is a 1, and the rest are all 0. That's what they're showing here. Then when you clock it, what's going to happen? Well, since the output of this is a 1, right, when it's clocked, remember, Q follows D, so it's going to bring the 1 into this flip-flop, right? So this is going to be 1, but the rest of them are all 0, right? This one right here came around and was the input of this, so when you clock it, this became a 0, right? That's what's happening. You clock it again, it moves over to the right. You clock it again, it moves over to the right. And then when you clock it again, this 1 is going to come all the way around and is going to again be right here. So that is a ring counter. You can think of it as a ring, right? The last output goes to the first input and its Q is connected to D, right? Pretty straightforward. Now let's talk about the Johnson counter. It's very similar. However, instead of connecting Q back to D, you connect the Q bar or the Q naught back to D, right? Now instead of showing the outputs through a series of pulses as we did here, I'm going to show it to you in a table. So if you start with them all 0 and you clock it, remember this Q0 over here, you're coming out of the Q naught input, so it's going to output a 1, right? Well, guess what? That 1 is going to come all the way around and be here at the beginning. That's just what it shows here, right? You clock it again, you see it just moves. Clock it again, it continues to move to the right. You clock it again, and now you've filled the counter, that Johnson counter, with all 1s, right? Well, guess what you can do? You can continue clocking it, then a 0 is going to come back. Continue clocking it, you clock it once more, you're right back at the beginning, all right? Now here's the thing you need to remember about these counters, other than the fact of how they're constructed. The number of unique states here is equal to n, right? Because there's 1, 2, 3, 4. So you have 4 unique states here before it starts to repeat itself, right? For the Johnson counter, you have 2n, right? That's an n there. There we go. Because if you notice, you're starting here at 0, right? 1, 2, 3, 4, 5, 6, 7, and you're back here at 8. So this total of 1, 2, 3, 4, 5, 6, 7, 8. You have 8 unique possibilities here, but you can have 8 clock cycles before it goes back to the way it was in the beginning. All right? I hope I stated that clearly for you. But that is a discussion about the ring counter and the Johnson counter.